Hey, how's everyone doing today? Howdy, howdy. Oh, that good, huh? All right. Okay, so let's get going. I wanna finish up the spherical coordinates today. So let's zoom through this. Alrighty. Okay, so spherical coordinates are probably the toughest one, the most complicated one, or maybe the toughest to get the hang of. But they're very, very useful. So he said, so in R3, we saw cylindrical coordinates are good for integrating over regions with radial symmetry. Or wait, maybe radial symmetry is the wrong. Maybe it's like axial symmetry or something like that. But symmetry about an axis, right? So like you have a cylinder, right, which is symmetrical. Usually we do about the z-axis for cylindrical, but you can do about other axes if you want. So stuff bounded by cylinders, sometimes cones, sometimes elliptic paraboloids, that sort of thing. Stuff symmetrical about an axis. So spherical coordinates are useful for, as the name would imply, integrating over regions bounded by spheres, and as we'll see, cones. But almost always, a sphere is going to be involved in the region if we're using spherical coordinates. So there's almost always going to be a sphere involved if spherical coordinates is the best coordinate system to use. And as we'll see, cones and sometimes points, but basically stuff involving spheres. If you see a sphere in there, almost always spherical coordinates is the best coordinate system to use. So we're in R3 as well. So polar is for regions in the plane, and then cylindrical and spherical are for regions in R3. So here's how spherical coordinates work. So points in spherical are going to be of the form rho phi theta. So the first guy's a rho, not a p. Okay, sometimes you'll see it as rho theta phi, but this book uses rho, then phi, then theta in that order, although it's not super duper important because we're not really going to be looking at coordinates of points. We're just going to be using this for integration, and you can figure that out. But anyways, or actually it does rho phi theta, which is, oh, sorry. It doesn't, hang on. It doesn't matter. It literally does not matter. So rho phi theta are our three variables for spherical. So here's what they mean. So Rho is going to be the distance of your point to the origin. So that's our rho. Let me actually just label it like this. So you take your point and you look at the distance to the origin, that's rho. So think of rho as being, so if your rho is like 2, your distance 2 from the origin, that means you lie on the sphere of radius 2. That's how we're gonna think about this. So phi is maybe the weirdest one. So it's the angle made with the positive z-axis. So here, this is phi right here. So think of it as the angle from vertical, right? So if straight up, if lying on the z-axis is 0, angle 0, phi equals 0, as you get away from the z-axis, as your angle declines from horizontal. So if you look at the line from the origin to your point, as that angle comes down from vertical, phi is going to increase. So the sort of confusing thing about phi is that angle there is phi, but if you rotate it around the z-axis, it's maintaining the same angle phi. So like if you look at the cone, whatever, you look at a point on 2 points on the cone, they're going to make the same angle with the positive z-axis, right? So this is still the same angle phi as the other guy had, even though it lies on the other side. It's still making the same angle, same declination from vertical. And we'll look more in that as we do some examples of integration. But phi is kind of the weirdest one. And you need to know phi always lies between 0 and pi, strictly between 0 and, or we never have negative phi, and phi never gets bigger than pi. So phi equals 0 is it lies on the positive z-axis. Phi equals pi lies on the negative z-axis. Right? You've gone all the way around to the bottom. That's the largest phi can be, is pi, lying on the negative z-axis. And we'll look more at that in a second. And theta is the same theta we've been using the whole time. It's if you project your point, so if this is x, y, z, if we project it down to the xy plane, so keep x and y the same, take z to 0, the angle measured counterclockwise with the positive x-axis is theta. So think of phi is giving you the angle made with the positive z-axis, and theta is sort of the angle measured around the positive z-axis. So how you're rotating around the z-axis with theta equals 0, meaning you lie above or below or on the positive x-axis. So same as before, essentially.
Professor?
Yeah.
I just have a quick question about rho. So, like, what would happen to it if, like, the sphere is not centered around the origin? Because wouldn't you get, like, different points on the sphere that are different distances from the origin?
Right. So rho equals a constant, we'll see, is going to describe spheres centered at the origin. Spheres not centered at the origin have different equations. But yeah, we just think of spheres centered at the origin. If you lie on the sphere of radius, did I not say centered at the origin? I should have. But like, so rho equals 4 means you lie on the sphere of radius 4 centered at the origin. Sorry, I should.
You probably said that. I just wanted to, like, make sure, because, like, so this is all just relative to spheres centered around the origin.
Yeah. So
okay.
Rho is distance to the origin. Yeah.
Okay, thank you.
Okay, so that's rho, theta, and phi. Let me redraw this real quick. So that's our phi. This guy is our rho. This is our theta. And so this guy here is a right angle. So we're going to get a relationship between x, y, and z, and then rho, phi, and theta. And these are a little tougher to remember, but there's sort of an easy way to remember how this works. Okay, so the shortcut I like to do is, so x, remember x and y are r cos theta and r sine theta in cylindrical, right? So we don't have r in spherical, but we can find what r is in relationship to rho and phi to memorize what x and y are. So this guy here, the distance of our point to the origin is rho. R, remember, you project it down to the xy plane and look at the distance of that guy, of the projection to the origin. That is r. So let's do a bit of trig to figure out what r is in terms of phi and theta. So this angle here, this is a right triangle that we have here. This angle here, as we said, is phi. And you can figure out geometrically, this guy here also has to be phi. So if we want to find a relationship between rho and r relative to that angle phi, so we want to see opposite over hypotenuse. Remember that's sine. So sine of phi is the opposite of phi, which is r, over the hypotenuse, which is rho. So that means r is equal to rho sine phi. So this is how I like to remember what x and y are, and as we'll see, z in spherical. So remember this bit, r is equal to rho sine phi. Okay, so x is r cos theta, and theta is the same in spherical. So r in spherical is rho sine phi, so x is rho sine phi cos theta instead of r cos theta. And then similarly, y in cylindrical is r sine theta. So in spherical, r doesn't exist, but it's rho sine phi. So this is rho sine phi sine theta. So remember that rho sine phi is r, and then x and y become easier to remember. And then z, instead of rho sine phi, is going to be just rho cos phi. Oops, it doesn't involve theta. So x and y, remember, are cos theta, are sine theta. Remember, r is rho sine phi. And then z, instead of rho sine phi, is rho cos phi. So these you absolutely need to remember. And then we also have, so x squared plus y squared plus z squared is going to be rho squared, which you could figure out by squaring everything and adding them up and doing some simplification. But also remember, rho is just the distance to the origin. So if you have a point x, y, z, x squared plus y squared plus z squared is going to be the square of the distance to the origin, which is rho squared. So you need to have those memorized. And also, this is also helpful because this comes up sometimes. X squared plus y squared is rho squared sine squared phi, which you could also do from simplification here. But remember, in cylindrical, x squared plus y squared is r squared, and r is rho sine phi. So rho sine phi squared is rho squared sine squared phi. But that one's not too bad. You can figure that one out if you need to. But x, y, z, and then x squared plus y squared plus z squared, you need to have those memorized. Okay. So really the important bounding surfaces we're going to be looking at are cones and spheres. So spheres centered at the origin are going to be the form rho equals rho naught. Rho is a constant. So that's a sphere of radius, rho naught. Centered at the origin. So the equation rho equals rho naught represents the sphere centered at the origin of radius rho naught. We're looking at all the points distance rho naught from the origin, and that is the sphere. So cones are going to be described by phi is equal to a constant. Or half cones, rather. And those are going to be the set of all points. So if phi lies between 0 and pi over 2, phi naught, we're looking at a cone. Oh my goodness. I'll take it, whatever. So if we're making an acute angle with the positive z-axis, that means our cone is going to lie above the xy plane. Right, that angle is acute. Remember we said phi equals 0 is the positive z-axis. What is phi equals pi over 2? So if we look at the set of all points which make a right angle with the positive z-axis, what is that going to be? How would you describe that? Not parallel to the xy plane, it is exactly the xy plane, right? Right, so the y-axis is going to be on there, the x-axis is going to be on there, and you just rotate those around, and you get exactly the xy plane. So think of phi as phi equals 0 starting at the positive z-axis, and as phi increases, you're opening up a cone, right? And as we get to phi equals pi over 2, now you've opened up like flat, and you're on the xy plane. And then as we get bigger than pi over 2, this one we don't do as often. So as the angle gets obtuse between pi over 2 and pi, now we're opening that cone up more, and now it lies below the xy plane. Right, now we're the bottom half of a cone, and it's going to lie below the xy plane. And then phi equals pi is just going to be the negative z-axis. So think of phi as starting at 0 on the positive z-axis, opening up a cone out to pi, and at pi, you're the negative z-axis. That's how I like to think of phi. Does that, any questions about phi? Because phi is what trips people up the most by far. Okay, so let's look at how to integrate. So the way we usually do these are so rho is going to lie between, actually, let me give myself some room. So we usually allow rho to be bounded by functions of phi and theta. But then phi and theta, we require those to be bounded by numbers. So phi lies between phi 1 and phi 2. Theta lies between theta 1 and theta 2. Suppose this is our region W. So if we want to integrate a function of x, y, z over this region W, so integrate with respect to volume. We're going to do exactly what we did in cylindrical. We're going to replace x, y, and z with their spherical equivalents. And then, so theta is going to go from theta 1 to theta 2. Phi is going to go from phi 1 to phi 2. Rho is going to go from rho 1 of phi theta to rho 2 of phi theta. So we go to our function f, and we replace x, y, and z with the appropriate thing. So this is going to be a lot of writing here. So remember, x is rho sine phi cos theta, right? So every time you see x, replace it with rho sine phi cos theta. Y is rho sine phi sine theta. And then z is rho cos phi. I underestimated how much room that would take. And then dv, this is the important bit. dv we replace with rho squared sine phi d rho d phi d theta. Right, so instead of d rho d phi d theta, you have to multiply that by the rho squared sine phi. So you cannot forget that. You need to multiply your function by rho squared sine phi. So like with cylindrical, dv was r dz dr d theta. In spherical, it's rho squared sine phi d rho d phi d theta. Okay. So it works exactly like integration in all the other coordinate systems, but dv is rho squared sine phi d rho d phi d theta. Alrighty. So let's do some examples. So let's calculate the integral over the region W of the function x squared plus y squared with respect to volume. Where W is going to be the region inside the sphere of radius 4 centered at the origin. Okay, so quick sketch. Always good to really, really quickly do a really rough sketch of your regions. Oh, that is my beautiful sphere. Of radius 4 centered at the origin. So everything inside of there is W. Okay. So we need to find the bounds for rho, phi, and theta. So for rho, we're going to do sort of similar to what we do in polar. We're going to draw a line from the origin. Through your region. And the closest surface, so the closest boundary surface to the origin is going to be the lower bound. We write that as rho equals something. Right, so the lower bound for rho is the closest boundary surface. The upper bound is the furthest. Right, so rho equals rho 2 of phi and theta is the outer bound. And remember, the lower bound, if the origin is in your region, rho's always bounded below by rho equals 0. So just remember that. If the origin is in the region of integration, rho's bounded below by rho equals 0, right? Right, because rho equals 0 is the set of points distant 0 from the origin, which is only the origin. So in this case, we draw a line from the origin through our figure. Well, the origin is in W, so rho is bounded below by 0. The outer boundary surface is a sphere of radius 4 centered at the origin. What is the equation of the sphere of radius 4 centered at the origin in polar, or sorry, in spherical? So it's a set of points distance 4 from the origin. Which variable tells us distance to the origin? Careful, that's R is not in spherical. So R is in cylindrical, but in spherical it's rho. RHO, if you wanted to write it out. Or you could just write P in there, and I know what you mean. So the outer boundary surface is rho equals 4. So rho is bounded by below by 0 and above by 4. Okay, so for phi, remember I said I like to think of phi as starting on the positive z-axis and taking the cone and opening it up. So at phi equals 0, you're the positive z-axis, opening it up until you hit pi on the negative z-axis. So starting at the positive z-axis, if you have points on the positive z-axis, phi is bounded below by 0. Right, so phi equals 0 is the positive z-axis. We do have points on there. And then opening up your cone, we're including all those points until we hit the negative z-axis. If you have points on the negative z-axis, phi is bounded above by pi. It's a little hard, a little less clear explaining that in this example, but in the next one, we'll see it better a better example of how this works. But does everyone see that? We have points on the positive z-axis, so phi is bounded below by pi, or by 0. And we open it up, and it's got all those points, and then we have points on the negative z-axis, so phi is bounded above by pi. And I won't spend too much time on this example explaining that, but yeah. And so theta, remember that tells us how much we go around the positive z-axis. Or sorry, how much we go around the z-axis, how much we rotate around. So we're getting the entire sphere here. So we're going from 0 on the positive x-axis all the way around 2 pi back around to the positive x-axis, because we're getting the entire sphere here. If we got, say, just the right half of the sphere, say where the bit where y is positive, what would theta go from? What would be the bounds for theta if I just get the right half of the sphere? Zero to pi, exactly. Yes. So if you can figure that out, then you understand how theta works. Okay, so we have our bounds for rho, phi, and theta. Okay, so I'm just going to set up the integral here. So we're integrating x squared plus y squared with respect to volume. So we said theta goes from 0 to 2 pi, phi goes from 0 to pi, and rho goes from 0 to 4. So x squared plus y squared, changing x to rho sine phi, cos theta, y to rho sine phi, sine theta. Remember we said x squared plus y squared. The easy way to remember that is that's r squared, and r is rho sine phi. So this is rho squared sine squared phi, x squared plus y squared. And then dv, we said is rho squared sine phi, d rho, d phi, d theta. So just multiply through by the rho squared sine phi. So we get rho to the 4 sine cubed theta. Okay, so really super quickly. So the inner integral, we're integrating with respect to rho. So sine cubed phi is a constant. Rho to the 4 becomes rho to the 5 over 5. And then evaluating at 4, we get 2048. Yeah. So 4 to the power 5 is 2048. And then sine cubed phi. And I just want to mention one thing, because this shows up sometimes. So if you're integrating sine squared or cos squared, remember we had the double angle formula that you want to convert to integrate those. But for sine cubed, remember sine cubed is just sine squared phi times sine phi. And sine squared is 1 minus cos squared. And the reason we do that is because we could just use sub, right? So when we multiply through, we get sine phi minus sine phi cos squared phi. And then we can integrate sine phi easily And we can integrate minus sine phi cos squared phi by letting u be cos phi. And then du is negative sine phi d phi.
Would we see something like that on an exam? Because
It's possible. It is possible. You should be able to do this. You'll probably see something like that on homework. If I wrote the exam, which I don't, but if I wrote the exam, I would have probably a problem involving this. I would this would be like a set up the integral type problem.
Right.
But you should know how to do that. Oh yeah, you'll get most of the points if you get the correct bounds and you write the correct integrand and do everything. If you set up the integral correctly but evaluate it incorrectly, you'll get most of the points for the problem. But it's still good to know how to do this. So at the end, we should get so just 2 pi times 4 over 3 times 2048 over 5. Whatever that is simplified. I want to do another example, so I'm not going to dwell on how to evaluate this too much. Okay, but the bounds for this one were really easy because it's just bounded by a sphere, right? And you get the entire thing. So rho goes from 0 to a constant, the radius of the sphere. Phi goes from 0 to pi because we're getting the entire sphere. And then theta goes from 0 to 2 pi because we're going all the way around, we get the entire sphere. Okay. So one more typical example that we get. Let's set up the integral here. So let's evaluate the integral of z with respect to volume over the region W. So W is going to be the ice cream cone looking region. I like to call it ice cream cone. So it's going to lie below a sphere. Right, that's the ice cream part, the sphere. So let's say the sphere is capital R, the radius of the sphere is capital R here. It could be whatever. And it's going to lie above the cone. Z squared equals x squared plus y squared. So as always, let's make a quick sketch of our region. So it lies below the sphere of radius r and above the cone z squared equals x squared plus y squared. So there's our cone. We're only going to look at the top half of the cone here because it's going to lie above this cone. And then below the sphere, that's really hideous there, but that's, hang on, let me do this. That's our ice cream cone region. Right, so the ice cream bit's the sphere, and the cone is the cone, obviously. Does everyone see that's the region we're talking about here? Okay, so we need to find the bounds for rho, phi, and theta. So for rho, remember we play the same game. So look at a line starting from the origin through your figure. Closest points to the origin, the boundary surface closest to the origin is the lower bound. Or if the origin's in there, 0 is the lower bound. Rho equals whatever is the upper bound. So the furthest away surface we hit, the outer boundary surface, is going to be the upper bound for rho. We write that as rho equals something. So the origin is in the region. So rho is bounded below by 0. What is the upper bound for rho? Careful, it's R, right? Because if we, so you can either convert the equation of the sphere into spherical and get rho by itself, or you can, that's probably the safest way to do it. Or you could just remember the sphere of radius R, centered at the origin, is just rho equals R. So if we converted this to spherical, this would be x squared plus y squared, but z squared, remember that's rho squared, is equal to r squared. And we always take rho to be positive, so that's rho equals r. Right. So rho lies between 0 and r. Theta is easy. Let's do that really quickly. What are the bounds for theta? So starting on the positive x-axis, are we going all the way around the z-axis? Are we getting the whole ice cream cone here? Or just like a quarter, the right half, left half, that kind of thing? We're getting the whole thing, right? So it's 0 to 2 pi. Going all the way around the positive z-axis, or the z-axis, period. Okay, so phi. So remember, always think of phi as starting on the positive z-axis at 0, and as phi increases, we're opening up a cone. And so the bounds for phi are going to be, so if you have points on the positive z-axis, phi is bounded below by 0. So we have the positive z-axis on there. Open it up until we hit the cone. And that's the furthest phi goes, right? So start at 0, open up until we hit the cone. We need to figure out what the equation of the cone is. Right, that gives you the outer bound, the upper bound for phi. So we need to write the equation of the cone in spherical. See, the equation of the cone we said was x squared, z squared equals x squared plus y squared. And let's write that in spherical. So z is rho cos phi. So z squared is rho squared cos squared phi. X squared plus y squared, remember we said that's rho squared sine, that's r squared, which is rho squared sine squared phi. We need to find a value for phi. So let's divide both sides by rho squared cos squared phi. So we can cancel the rho squared top and bottom. And we have sine squared over cos squared equals 1. And so let's take the square root of both sides. So sine phi over cos phi is plus or minus 1. So for what values of phi is sine phi over cos phi positive 1? Remember, phi has to lie between 0 and pi. So for what value of phi between 0 and pi is sine phi over cos phi equal to 1? So for what angle phi are sine phi and cos phi the same?
Pi over 2.
Not quite. It's pi over 4. So pi over 4, they're both 1 over root 2 or root 2 over 2. So for pi over 4, sine phi over cos phi is 1. And for negative 1, for what angle between 0 and pi is sine phi over cos phi negative 1? Remember, it's got to be, that is true, but it's got to be between 0 and pi. So the angle between 0 and pi is going to be 3 pi over 4. Okay. So it could either be pi or it could be 3 pi over 4. But we know we're looking at the upper half of the cone, right? So for phi equals pi over 4, that's going to lie above the xy plane. That's an acute angle with the positive z-axis because pi over 4 is acute, and so it lies above the z-axis. That's the piece we want. Phi equals 3 pi over 4 is the other half of the cone, the bottom half, but we're not concerned with that bit of the cone. Oh, come on, dude. So phi equals pi over the 4 is the half cone we're looking at. And so that's how we get the upper bound for phi. We open up until we hit that cone. We need to find the equation of the cone. Well, it's phi equals pi over 4. Does everyone see that bit? That's really important that you understand how to do that. You take the equation of the cone, you convert it into spherical, and then you solve for phi, essentially. Because the cones are always going to be phi equals a constant. Okay, so let's just set this guy up and then end it there. So the integral over W of z with respect to volume. Okay, so we said phi or theta goes from 0 to 2 pi. Phi, we said, goes from 0 to pi over 4. And rho goes from 0 to capital R, the radius of our sphere. Z is rho cos phi. And then dV becomes rho squared sine phi d rho d phi d theta. And so just multiply through by the rho squared sine phi. So we get rho cubed cos phi sine phi. And that's not a difficult integral to do. When we get to phi, cos phi sine phi, you can just use sub. And we should get pi r to the 4 over 8. for our answer. Okay. Any questions about spherical? Just make sure you understand how phi works. That's usually the one that trips people up. All right, cool. So that's it for integration in polar, cylindrical, and spherical. We'll look at applications of multiple integrals next time, mainly center of mass and mass of a thin flat plate. And yeah, and that'll be it for the material on this upcoming exam next week. So yeah, I'm going over to office hours Zoom, and have a good one, guys.